In this video we're going to be going over a molecular view of water and also water bonding. And this is our part 16 video inside of chemistry chapter 2. So let's get started with this video. So starting off, we're going to talk about the molecular structure of water. So the properties of water at the microscopic level are influenced by two main features of the water molecule. And the first one is shape, and in the next slide we're going to talk about the second point. So considering shape, the water molecule has a bend shape, which is attributed to the arrangement of electrons within the molecule. And we can see that on the right on this picture here of this water molecule. And this bend structure of the water molecule is due to the oxygen atom attracting electrons more strongly than the hydrogen atoms. And this results in electrons spending more time near the oxygen atom than the hydrogen atoms. And this is also why the oxygen has a minus, because it's attracting those electrons. So that's why it has a negative charge, and that's why these hydrogen atoms have a positive charge. And we're going to talk more about this in the upcoming slides. So moving on to the second point is bonding. So the water molecule consists of two hydrogen atoms and one oxygen atom connected by two OH bonds, which are polar due to the uneven distribution of electrons. And this polarity means that the oxygen end has a partial negative charge indicated by the minus, and also the hydrogen end has a partial positive charge, and that's indicated by the plus. So we're going to talk more about polarity and polar bonds in the next slide. But before we move on to the next slide, the water molecule basically consists of two OH bonds, which is a OH bond between the hydrogen and the oxygen. So moving on to polar bonds. So the OH bond has a permanent difference in charge across it, which makes the bond polar, with the oxygen having a negative pole and the hydrogen having a positive pole. And this leads to the overall molecule having a dipole movement, which means it has two poles, a positive and a negative one, as illustrated in the figure included on the page. So as we said before, in this picture we can see that the oxygen has a negative charge while the hydrogens have a positive charge. And this is due to the permanent difference in charge across it because of the polar bond. So now we're going to talk about the attraction between water molecules. So polarity and attraction. So the polarity of water molecules with the positive hydrogen end and the negative oxygen end lead to mutual attraction between the molecules. And this interaction occurs when the positive hydrogen end of the molecule attracts the negative oxygen end of another, and this forms a hydrogen bond. So what there is here, so we already know about the polar bond, which is the difference between the oxygen, which is the negative, and then the hydrogen, which is the positive. And then what happens is that there's another bond, which is called a hydrogen bond. And hydrogen bond is basically where there's the positive hydrogen end of one molecule, and that attracts a negative oxygen from another. So if we look at this figure here, we can see here that there's at the top, here's one molecule of water and there's another one here. So you can see that this one hydrogen end, this positive hydrogen end, is attracted towards this oxygen. So this is called the hydrogen bond. And you can see everywhere else, they're all connected to a hydrogen. So hydrogen and oxygen are always connected. So furthermore, talking about hydrogen bonds, these are a type of intermolecular force like covalent bonds that act within molecules. And as we explained, hydrogen bonds are basically where this hydrogen is connected only to one oxygen, and that oxygen is connected to another hydrogen, and so on. So an intermolecular force, on the other hand, acts between atoms within molecules, and a covalent bond is an intermolecular force. So a covalent bond is basically where you have two different metals, and then they share electrons, and that is what a covalent bond is. However, a hydrogen bond, as we covered, is what we just explained, so where the hydrogen connects to the oxygen. And then furthermore, for hydrogen bonds, these are the strongest of the intermolecular forces. But however, they are also much weaker than covalent bonds and also, of course, ionic compounds. So what we're seeing here is that hydrogen bonds are still the strongest of all the intermolecular forces, for example, which we covered over here, but they're still weaker than all the covalent bonds. So now moving on to the unique properties of water, we're going to talk about the boiling and melting points. So water's boiling and melting points are higher than those of similar substances without hydrogen bonds. And this is because the hydrogen bonds between water molecules require a significant amount of energy to break. And now we're going to take an example of something else that also has hydrogen bonds. And this one is ammonia, which is NH3. So ammonia molecules do form hydrogen bonds, but they are not as extensive or as strong as those in water. And ammonia also has a boiling point of minus 33 degrees Celsius and a melting point of minus 78 degrees Celsius. So what we're saying here is that water's boiling and melting points are higher than any other substance without hydrogen bonds. And even if they do form hydrogen bonds such as ammonia, they have different properties as water, and they're also not as strong as waters. So furthermore, we're going to talk about the energy requirement for temperature increase. So it takes a substantial amount of energy to increase water's temperature. And this is due to the need to overcome the strong attractive force of the hydrogen bonds among the water molecules. And as water cools, it also releases a great deal of energy. So now for the concave and capillary action. So water forms a concave arc and also exhibits capillary action when it's in contact with the sides of the container. So this basically means that if you pour water inside of any container, it's always going to have this type of a round shape. So you're not going to see it really well. And also it depends on the type of container that you have sometimes, but you're usually going to see the water sticking towards the edge and then you're going to see water going in a curve, and it's not going to be just flat. And these properties are due to the attraction between the polar water molecules and the container sides, which also explains how water is drawn up from the roots to the leaves of a tall tree. So now we're going to talk about the buoyancy of ice. So ice is less dense than liquid water, and that's why it floats on top of water. So if we take an example of a lake, during the summer the water is just there and it's just sitting on top of the lake. But once it turns winter, then a thin layer of ice goes on top of the water. And since it's on top of the water, that means ice is less dense than water itself, and that's why it floats. And this is because water expands as it freezes. And then once it expands, the molecules also arrange themselves in an open pattern stabilized by hydrogen bonds. And now for surface tension. So water exhibits high surface tension due to hydrogen bonds pulling water molecules together at the surface, minimizing the area that they cover in general. And this effect is observable when a small volume of water forms a droplet, creating a circular shape as it falls through the air. And that summarizes everything for this video, so we're gonna just go over a quick summary of what we learned. So we talked about water molecular view, we talked about its physical properties considering molecular aspects, and in our next video, we're going to talk about some practice questions on this topic of what we covered in this video. So that summarizes everything for this video, so thank you so much for watching from Try to Be Useful, and we'll see you in our next chemistry video.